Is the other one off? Okay. All right. So my name's David Ahern. I work for Infabrica, and I wanted to present something that I started when I joined Infabrica very early into the company, and we had to kind of get moving on both things at once, and I came up with what I thought were some clever tricks to help us get our software driver side going and software stack going, and wanted to share some of what we had done as a company with everyone else, because like I said, I think it was kind of cool way to get moving and not be held up by some of the hardware side of things. So to set some context and motivation, it is the idea that you've got this great idea for some new piece of hardware, and in this case it's an Ethernet device, and you want to turn those slides and ideas into something real, and you want to do it quickly. And so what that means is, you don't want to get hung up by the hardware software interface. And at the beginning of time, you have nothing defined there, right? You have no existing software to extend or adapt. You have no existing hardware software APIs, no descriptor definitions, no CSRs, nothing. But you want to get moving, and you want to be able to do this parallel hardware software development, okay? And then also, as you're doing your own work, there's things out in the open source mailing list that are happening, and you want to be able to do some POCs very quickly. How does this ZCTAP proposal align with what you're doing, for example? Or the current patch sets around Linux DevMem with the GPU memory. How does that kind of fit into what you're thinking within your own company, right? And again, you don't want to wait for the hardware support or APIs or any of that kind of stuff to be defined, because you're just trying something out. And so how do you get moving? And based on some conversations at NetConf, I realized very quickly I really do need to set this context and motivation to what we were doing and why. Because most of the hardware people at NetConf were like, well, of course you use QEMU, but again, this is the beginning of time. So for QEMU, you have to have some hardware definitions, right? You're going through the PCI interface. So the QEMU model most definitely has its value, but not at square one, right? And really it gets down to this idea that the PCI interface is not unique to your device. Sure, the CSRs might be, but the DMA operations, the MSI operations, the bar management, all that kind of stuff is needed in time, but it doesn't stop you from getting moving with your data path and your descriptors and some of the basic infrastructure that goes into what does it mean to be an Ethernet NIC driver, right? So anyone who's done any kind of software development for a Linux driver knows there are many, many, many Linux networking APIs, Ethernet APIs that can be coded from that kind of the hardware interface up, get all that infrastructure in place. Start building your unit and integration and end-to-end test cases, getting all that infrastructure going. And then, depending on what you're building and what its extensions are, you can start working on a related software, something like SDKs, or if you're doing RDMA and IB kind of support, get that IB module and provider going, et cetera. It's all that surround software that goes on top of whatever you're building. And the key is to focus on what is important now. And that's like the design of the queue descriptors, what the requests are. If software had some dream things to ask of the hardware team, start getting those understood, so you can start weighing the balance of, well, if you take this away from me, well, software has to react by doing such and such, right? And so it is going to be that trade-off as you're developing something. And then focusing on getting that software architecture development, the test environment and stuff, getting confidence in what you've written and in that ability to do it on a very simplified model. So when you're the engineer who wrote the hardware side of things and you want to do a test, you can very quickly go in and make some changes. And, well, if I do this, what happens? Or you can do some failure modes where if this fails, what does that mean to the software stack? And I got an example of that one at the end. All right, so from a prior art perspective, it's really an extension of things that exist, which is kind of true for most things. So if you look at vETH devices, right, that's the existing capability today for containers. right? You can do networking inside of a namespace. It's not tied to a PCI device. So it's got a very simple device model, which is a packet that is TX'd by one vEth device in one namespace is just forwarded and handed off as is to another. Yeah, there's some scrubbing going on in some of the metadata, but the actual packet itself, it's just like take it from one vEth device and drop it onto the other one, and then it ingresses into the networking stack as if it had just arrived. But such a simple device model has allowed some very complicated software testing. Using namespaces, using the device, you can build really complicated data paths and end-to-end software tests for functionality. So if we were to extend that a little bit, what we're really talking about is putting a kind of a device model into like a vEth driver, where when that SKB comes down the stack and hands off to your driver for that Netdev, that transmit function isn't going to take just the SKB and hand it off to its peer. It's going to actually fill in the descriptors, right? So your driver is going to have some queues with hardware, and that hardware, those descriptors, or the queues rather, are going to have a format, some descriptors on how it's going to convey information to hardware, right? Some metadata about the packet, references to the buffers representing different fragments and stuff that's in the SKB. And then you submit that to hardware by hitting a doorbell, moves the PIDX, for example. Hardware says, oh, I have something to go take care of. It's going to do some processing to it, and then it's going to hand that off to a network switch. Well, in this case, you know, if you're doing a vEth style, it's going to be a peer-to-peer. So if it's TXing out one, and you've got a direct connection to another vEth instance, and so you could just hand it off. But it doesn't have to be that way. You could just as easily have multiple of these instances, and you would have some kind of more complicated forwarding lookup, whether it's a simple peer-to-peer, a switch model based on DMAX, or some kind of a routing model. In the end, I only ended up doing just the vEth kind of pairing, where there's two of these instances and they're doing a directly connect. But you can also leverage something like tap device to get that other side of things, where you're doing the bridging and the routing and doing the complicated setups. And so when it comes to that trade-off on time, I found the ENF instance. So I guess to back up, when you're developing a driver, for example, you have to have a nice namespace for all of your functions. And since the name of our company is Infabrica, ENF is that prefix for everything. So when you see ENF somewhere, like that's ENF 0 means that's our first device the driver is recognized. Or ENF in some of these function names, that's just our name spacing on some of the code. So anyway, when you start looking at what tap device can do for you, the tap driver has a nice ring to it. So when packets are being TX'd from the tap device going to whoever owns that ring, it'll drop the packet into the ring. The owner of that ring is responsible for pulling packets off, and that becomes the wire into your device model. The TX side of that coming out of your device, which is RX into the tap device, is a kernel send message. And for those who haven't done a lot of tap-based programming, that gets really confusing fast because it seems like all the functions are kind of backwards, but you have to think about it from the perspective of the tap device. So anyway, what this combination with a tap device and your device model brings in is you only have to work on one path at a time. And that made things a lot simpler to do some validation to make sure what you've done in your device model is coded properly. So for example, if you've messed up the checksums or your TSO slicer isn't generating the packets correctly, you know, you've only got one path to sit and debug, and that tap device provides a nice way to get access to the packets that are coming out of it. All right. And so when you're developing a driver, some of the essential elements that you have to deal with, generically speaking, the host stack sees a PCI device, and then there's these PCI dev operations that the driver has to handle. From there, you're going to have a Netdev representer, which is your way of presenting your device to the Linux networking stack. The Netdev has all kinds of net and NDO operations and stuff that it has to implement to say what does it support and how's it going to implement things. You've got the queues, which represent some host memory and your way of talking to hardware, where you're submitting packets to hardware or receiving packets from hardware. You've got features like flow steering and RSS. You know, how do you decide which packets are going into which queues? So anyway, these are the kind of the things that we're going to focus on to get started, to get the guts of this driver up and going. Now, when you're doing your hardware model, you have to decide, well, what elements am I going to put into this? Because you obviously can't make an infinitely correct device model in software. It's just going to take way too much time. So what are the important attributes that matter for your own testing side of this? So for example, when you're doing, starting on the TX side, you submit a packet to hardware. Hardware has to decide what the TX scheduling algorithm is, right? So if you've got a bunch of TX queues, it's got to pick which one is it going to pull a packet from, how many packets is it going to pull off of it. You want to enable things like TSO, especially if you're doing any kind of high performance. You want to be able to submit big packets down. And so that means your device model has to be able to slice those into wire-sized packets. For that side to happen, you have to advertise that you support checksum offload, right? And so that means you have to implement some kind of checksumming on the packets, whatever protocols you're supporting. And then you got to put those packets onto the wire, which means you're going to transmit it to some other thing, and then that other thing is going to receive the packet. At the top, it's going to have to decide which queue am I putting this packet into. Well, to do that, you need to have some kind of RSS and flow steering. Well, to do RSS and flow steering, you have to have hash. Hash over some header fields that you're using to pick your queues. Well, to do a hash over headers, you have to have some kind of packet parsing, right? And so this kind of gets into these basic elements that you're going to implement in your device model as you move a packet from a TX side to an RX side and back. Right, so again, these code paths that matter now, the PCI device operations. Now, for your software model, there's nothing you can really do. There's no real PCI device here. So you just stub those out, okay? But you're putting the code, you're making the code ready for hardware so that when the actual QEMU model or even the actual hardware comes around, you're just simply switching the model that's compiled in, enabling the stub so that you're actually calling the PCI things like, setting the master, enabling the device, setting your capabilities, doing your MSIX, all that kind of stuff. So your driver can work in both of these environments just by stubbing things out. You've got those devlink operations. If you're planning to do any kind of devlink based management of the device, you can go ahead and set that up now. The Netdev representative, like I mentioned, you get into the whole control path representation of how are you going to manage queues, and whether that's creating a single queue set or creating a queue set across CPUs, or even extending it beyond, like I said, if you're doing some kind of maybe IB support where you want to be able to let applications create those queues. And so you have to have some kind of queue management model going. All right. And then, of course, we got ETH-tool APIs, tons of ETH-tool APIs around information and coalescing and what does the driver or what does the hardware do and those flags, flow steering, the hash table indirection, all those kind of things can get set up because you've got your basic queues, okay? The code paths that matter from day one, right? Again, it's those descriptor formats, like how is software submitting things to hardware? What information are you expecting to tell hardware? What information are you looking to get from hardware? From an RX perspective, for a packet to land, you have to post buffers to hardware. Well, that means you got to do memory management, which gets into the page pool API, okay? So without even having a real device or a QEMU model, you can go through and start coding up the entire memory management aspect of buffers going through the page pool API. You have the completion handling and NAPI. All of that can get done. From a TX perspective, when hardware says, yep, I'm done with this packet, I've sent it, you get the completion back, and now you can start freeing the SKBs. You can get all that kind of logic coded up and tested. And a big one to me is you really don't want to rely on packet injection. You really want to rely on a closed loop path. It's just so much easier to generate different traffic patterns or traffic types, payload types, and get into secondary aspects of it. So for example, if you're looking to do zero copy, or if you're looking to see what happens when retransmits happen, or if you're looking to see collisions of flows and you know, multiple things are going on, having closed loop data path is a big part of that. Debugging and monitoring, trace points, heavily rely on trace points, and the eTool API is another one. And so those eTool-S, where you're getting the driver and hardware specific stats, that's something that can all be done now. And so that's the key point, is you're able to get a lot of your driver infrastructure in place and ready for the extension for the hardware details without waiting and being serialized behind what the status is of the hardware and where the CSRs are being defined and what that interface is to the firmware around the messaging and the formats of those messages. So, you know, this is a hindsight presentation as well. I can't say that what I'm talking about here is really three years and 3 months later, and the code has evolved into what I'm discussing here. Unfortunately, I had to learn my own lessons and stuff, and that's why I also wanted to make this out to the community as hey, here's some clever things that we've learned over the years and how to make this even simpler. So if I were to do this again, I wouldn't have to relearn some of these lessons. I could just jump straight to what I know I'm going to need at the end. And so the key to that is having a hardware abstraction layer where if you're compiling in the hardware, the real hardware side of things, you would bring in that file on the bottom left. But if you're just doing a software development testing, software only model, then you would bring in the stubs and your testing environment would get brought in. But your entire software stack, everything from that hardware interface up, whether it's the IB driver, your SDKs, your Netdev driver, et cetera, they all see the same APIs. It's just what happens at the bottom end is what changes. And of course, there are some very subtle details in there, one of which is software model operates on virtual addresses, hardware model needs physical addresses or DMA addresses. And that one was probably the trickier one to have to compile around. All right, so now to get started, very beginning of a module, you got to have your module init and your module exit. For the module init for the hardware model, its basic job is to register your device driver, your PCI driver with that subsystem, and says, here's all of my device ops, my probe, my remove, et cetera. Well, software model doesn't have a PCI dev. So what you do is you just allocate one, just a data structure, right? And then you fake out the PCI probe function. Now, what the software model is going to have is some way to monitor. You have all these queues that are being created, some TX, some RX, maybe some other ones that exist. And something has to check those to say, hey, is there a packet that I need to transmit? And you do not want to do that in line. If some process is submitting a packet, you don't want to pause all that execution and have it go run the model, run the packet through the model and drop it into wherever the peer device is. So instead, we have a K-thread that kind of polls and then does a SCAD timeout and then polls and does a SCAD timeout. And that's more so that you don't lock up a VM trying to do too much when you're trying to send a single packet and check everything out. And meanwhile, your Chromebook or whatever you're working on is smoking because you've got something pulling a CPU without a break. So anyway, some key points there is that a kernel thread that does the polling, but also will take a break and do a SCAD timeout. And I will also tell you that really messes with the SRTT for a TCP connection too. So there are some limits of what you'll be able to do performance-wise with this kind of a model. All right, so that device initialization through the PCI interface. You know, your physical hardware is in a system. That device ID is going to show up. It's going to see your driver handles it, and so off it goes calling your probe function. So if you're going to fake that out from a software side, what you want to do is wrapper all of those PCI init functions into one that's, again, it's in that HOW layer, where in this case, the ENF PCI init has two different implementations. One, the software model. The only thing it's really got to do is set the private data on this faked out PCI dev struct that you've created. Where the hardware side is this going to actually have to go do some PCI calls to kind of set this device up. So the DevLink ALEC sets this thing up so that we're ready to roll with DevLink infrastructure. So you register it with DevLink. And then there's the Netdev representation there. So the ENF Netdev is really what just is the standard initialization for an Ethernet Netdev. Some basic things where you're doing around your eTool operations, your NDO operations, your MTU, max-min, all that kind of stuff. And then tell the networking stack about your new NetDev. All right, so this is where kind of some lessons learned. So test priv is our, I guess that's really the ENF test priv. This is this private data structure that goes with each PCI device. And so as you're doing these basic functions inside the model, it's invoked with the PCI dev as your kind of top argument because maybe you have multiple of these devices in a system, and so everything's relative to that one instance. And so we ended up at the end with test priv is a container of PDEV, so the PCI device. And then you have all that metadata that goes. For example, this PCI device will have X number of queues, X number of TX queues, X number of RX queues, some completion queues. And when you call into the device model for a particular queue ID, you'll have access to the PCI dev, which then container gets you the test priv, which gets you access to your set of queues that go with that device. Let's see. Platform device was a huge part of this. It gets you that struct device that a lot of internal kernel calls need when you're dealing with hardware. The platform device framework provided a really good way to handle that side of it. And so that's what you can see here with the platform device ALEC and the platform device add. And that becomes that basis for your some of the hardware function side of things from a PCI perspective. And then you call your PCI probe function, which again does the real thing on hardware, does nothing on software except set the private data. All right, so now we get into notifications, IRQs. That was kind of a tricky one because you want to have all this again. You want to have it set up where the same code works on both platforms. So how do you fake out this idea that an IRQ needs to fire? Your software test model filled in an RX queue and wants to send a completion. That completion has an IRQ tied to it. The IRQ was a fiend to some CPU. Well, you can have all that infrastructure in place. Your IRQ management, affinity, the IRQ handler, all of that stuff goes down. And so when you're doing that management side of it, like for us, it's ENF request IRQ, the software model of that just tells the testing metadata, kind of saves it that says, well, when you do a completion, or when you want to fire this IRQ, you want to do it on CPU 1, CPU 2, whatever. And then you use the SMP call on CPU to make sure you're invoking that IRQ handler on the right CPU. And then the IRQ handler is basically just going to call nappy schedule for networking. The other one from a hardware interface you got to deal with is the doorbells. And again, this is where the HAL wrappers come into play. If you're doing your hardware version of it, it would call into the CSRs, which is going to tell hardware, what the new index is for your TX queue, for example, or your RX queue where you're submitting buffers. And then the software side of that, you're just going to call into your testing model. Whatever your software model is, you just call it, but you don't, again, want to deal with packet movement at that point. All you're going to do is update the index in that metadata structure. When that next time the K thread wakes up, it'll say, oh, there's a TX packet for me to go move, or oh, there are some RX buffers that were posted. Let me go check and see if I need to go retrieve those, for example, right? Okay, control path. Again, you're going to want the ability to manage queues, like multiple different queue sets. So again, for us, it's not just the core driver has, is in a VM that's running 8 CPUs, and so we're going to create 8 queue sets. We also want the ability to create queues for other use cases, right? So for example, some of these zero copy patch sets that have been posted, that ability to create queues on the fly is kind of essential to what you need to do in terms of a simpler, robust solution. And so go ahead and do that now. Create your queue sets where you have all the operations you're going to be doing on the hardware side, and then now you can do this on the software model as well, okay? The hardware model itself, you'll actually go through and do the create queues in your hardware. That's probably a message to a firmware that says, hey, I need such and such queues. Here's the address of the host memory where you can find that queue. Here's how many entries are in it, and here's my initial state, right? So PIDX is 0, CIDX is 0. Meanwhile, on the software model side, this is one where you actually will just step into the software model and just actually say, hey, I'm going to allocate a queue for this based on, here's my queue ID, and go ahead and set this up so that when a doorbell or when an IRQ request comes through or something like that, you have all that metadata set up. The infrastructure is there for the software side of things. Okay, so now to actually start walking through some of the details. Starting with the TX path. Excuse me. All right, so the networking stack, routing is pointed to your device as the TX device, as the exit. And so your NDO start transmit gets called. So it comes down to the driver. Well, if you're on hardware, the driver is going to look at that SKB. It's going to see it has so many fragments. It's going to have to DMA map each one of those fragments, those kind of operations. So you can't do DMA mapping for software model. So again, put a HAL wrapper around that where it does nothing for your software model. You do have to save a reference to that SKB completion so that the SKB waiting for the completion. So the hardware model actually has to go DMA the fragments and actually send that packet out and then send you a completion. Your software model also, because it's operating asynchronously, will have to get around to that TX queue, send the CQ up to the software, do that fake IRQ, and then your completion handling can kick in. So it's like all of that kind of stuff, all those little nuances can be handled, again, in a purely software environment only. So software model, the data path, like I've said, this K thread is kind of sitting around, and every once in a while it'll wake up and decide it's going to do some iterations over all these TX queues. And maybe in that millisecond, 5 TX queues have different packets queued up. You have to decide how you want to pull from that. Are you going to do one-to-one, kind of equal weighted round robin kind of a thing? But what if that's a TSO packet? Are you going to account for that size of the packet in the logic? Because taking a 512 kilobyte TSO packet and turning that into, 8,000, I forgot the number now, the number of 1,500 byte packets, that's a lot of CPU cycles that are spent slicing that up into wire packets. And so your other queues are going to be getting starved. Or do you kind of take breaks in how you're processing each one of those TX queues that have things ready to roll? One lesson learned from this was always leverage the kernel KVEC and its helpers. Take everything and turn it into an IOV. And then you don't care about what your peer is. You don't care about how the packet was handed to you. So if the headers are split across multiple fragments or multiple IOV entries, your logic doesn't handle it. If you expect one big buffer, inevitably you will get a packet. Well, that's not going to work. So pro tip, lesson learned was to make sure you're using IOVs. Again, if you're leveraging the tap device for your forwarding, for your peer device, you would call kernel send message with that IOV. That then is going to take that IOV and turn it into another SKB and send it up the networking stack so that whatever it wants to do routing-wise from an ingress perspective happens. If it's the same type, then you get this IOV, and you're going to go look up which RX queue it's going to land in by going through your device model, doing your packet parsing, doing your hashing, doing your queue lookup based on whatever has been configured for your RSS, your flow match. Right? So if you've got a precise match, for example, maybe it is like the TCP Linux DevMem patch set where it's got a precise flow and you got to make sure you're using exact queues. So you've parsed the packet, you've picked that queue, filled in the descriptors, landed the packet where it's supposed to go buffer-wise, and then sent the completions for both sides, one for the TX side and one for the RX, to say, hey, you got something to go look at. Data path RX, I guess I kind of went ahead of my slides there. So again, for the RX path, you can do the entire coding, and the only shenanigans gets into that IRQ handling, because what you really care about is getting the NAPI schedule handled, or getting that scheduled so that it'll invoke your NAPI polar, so you're processing the RX rings based on whatever CPU it's allocated to or assigned to, and however many packets your budget is for that particular instance. As a part of that, you pushing the packets up into the networking stack and then pushing more buffers down to your hardware, to your software model side of things. Again, from the TAP device versus, what is your peer device? For the TAP, you go into that ring and you kind of say, hey, do you have anything else for me to deal with? Because your TX from the TAP device is your RX, so you're pulling something off of that ring, doing that conversion to the IOV, taking the IOV, going through your software device model, landing the packet, and going up the RX stack. One thing to note about the software model side of things, hardware will DMA into the posted buffers. Software model, you have to do a mem copy, and that mem copy is what's basically going to limit your throughput. So on a modern CPU, like what I've got is it's a Ryzen 3. 5 gigahertz Ryzen 3, and based on your MTU, it gets around 15 to 30. I'll show you a demo in a few minutes where I have the MTU at 9,000, and I think I was getting almost 40 gig. But pretty much that is the limit based on just the CPU peg doing a mem copy. But it's a software model. You don't always have to copy. For example, iPerf3 is a benchmark. Payload doesn't really matter. So if you had a way to flag those iPerf3 packets and said, you know what, don't worry about copying the payload. I'm more interested in the semantics around stress testing the process to driver down to hardware back up to other process. I want to stress that software stack. The actual payload that's being moved between these two instances, I don't really care about it. So then skip it. Skip the mem copy, get a higher throughput. That higher throughput allows you to cycle through your rings a whole lot faster, so you can make sure you're keeping up, that you're not losing packets because you've got nowhere to post it because you didn't push buffers out fast enough, or maybe your rings are too small for really high bandwidth workloads. And then from that point, you have an established driver. You've got RX working, you got TX working, your control path is all set up. Now you can start working on all that other extra infrastructure, things like the trace points and your debugging infrastructure, which is going to help you identify problems. And that's really what matters. Like the beginning part of this is so mechanical from the standpoint of getting the different APIs coded up. That's the mechanical piece of it. Your actual hardware is the unique piece, and then how are you going to do your debugging? And so some of these faster networking devices, you can't rely on things like strace or TCP dump or these other legacy monitoring tools. You really have to rely on faster things like trace points and an equivalent to XTP dump, for example. So if you get access to your packet through a trace point, you can do an XTP dump style PCAP. You start working on that infrastructure now. And if you're doing some IB related work, you can get that stuff going, get the IB driver going, get the IB provider going. If you're doing machine learning kind of applications, all those plugins, you start working on all that other stack while your hardware is still in development. Okay, so before I go into the demo, the advanced use cases, like if you look at VE, you can really create some complicated tests. You can do ECMP testing. You have multiple namespaces kind of linked together through routing, through bridging. Well, if you choose the ENF to ENF kind of a style, you can do multiple sets of those where one ENF goes into the other, its peer, which is connected to a bridge, which is connected to another, which you can do those kind of topologies. Or you can create, with TAP device, I was using a router interface for a while because the Linux stack would validate the checksum for me, because if it didn't, check out, it wouldn't forward the packet. And so I'm like, oh, well, I got a problem. So let me go figure out what I broke and some change. Let's see. Yeah, I think that's all of it. And I'll come back to that other, the advanced kind of failure scenarios you can get into. All right, and so with that, let's go look at a demo. All right, oh, I do not want to shut down. I want to do the Netdev demo. Is that large enough? Okay. I did not record it this year after last year's debacle with AV. All right, so the first thing you got to do, load that kernel module. There's no PCI device, so no one's going to load this thing for you, so you have to go and load it. What I've told this thing to do, this setup script, is load the ENF driver. I want 2 devices, which means so I have a peer, like a VE style peer. There's a testing namespace where there's one, the init namespace has ENF0, the testing namespace has ENF1. So you do a IP link show, it'll show you both devices. You can see the one in the other namespace. If you look at the details, like there is no name to it. Like this is really going after the PCI style representation of a net device. You can give it the address at the MTU, all those kind of things. etool-I, again, you start working on those etool APIs well before hardware is even thought about how it's going to, the QEMU models even thought about how it's going to work yet. Firmware version, well, we don't have firmware here, so I'll add it when we get there. And you can see the bus info there shows you that platform device. So that gets into the whole struct device infrastructure being implemented by platform device. So this is DevLink status. If you do DevLink show, I think, or DevLink dev show, again, I've got 2 devices. These things are all set up, ready to do whatever extensions we want to do. If we want to do resource management, we want to do parameters, we want to do what have you, all that infrastructure can be developed in this software-only environment. Oops. Let's see some actual closed-loop connection. So I bumped the MTU to 9,000, and here we go. This end-to-end TCP stream is going. I could show you, like, I don't think it's a secret. After last NetDev, we showed that we had this IB infrastructure. You can run IB apps against these 2 NetDevs where it thinks it's actually dealing with hardware. Provider loads up, starts up does all the create queue pair, all that kind of information, and then it'll transfer a file, for example, just as a silly way to do a demonstration of an IB application working. You can do etool-S, so all those lovely stats that people are going to want to do some kind of monitoring. Is the packet landing where I think it is? Is it being transmitted evenly across queues, for example? All that kind of infrastructure, coded, tested out, checked. All right, and that was it. And so the next thing I wanted to show was, as a part of having a software-only model, it's super easy to do random hardware failures. For example, you got a packet socket application. And this is something that happened, I think it was last week or 2 weeks ago. You have a packet socket application. It's sent the packet and it's waiting for a completion. What if that completion never comes? What happens? Does anyone know? The application will sleep happily. It'll stay there forever until it hits a signal. If you Control-C it, hey, what's going on? The application won't terminate. It goes on an infinite loop, and it just locked up that CPU. So clearly there's some kind of a bug. We haven't had time to get into it. It's this guy. Right, so it sent a packet. It was a bad packet. There was a bug in one of the models that it said, oh, this is a bad packet. I'm not going to send a completion. And so the application's very happily sleeping. right? So it's just sitting on a SCED timeout saying, let me know when that completion finally comes in from hardware. Whoops. Well, like I said, it was a bad packet, so I have the model set up to ignore those. So, all right, let me try it again. I'll Control Z it this time, put it to the background. I am surprised that it stopped, but here's the lockup. And if you go and look at it, it's just stuck in a loop. Because there's a signal, it won't go to sleep, but because it didn't get the completion, it won't return. It won't go back into user space. I have to go figure out why that was the first time a Control C actually worked. It's probably because I went through sudo. So anyway, that's the kind of stuff you can get into when you have a pure software model. You can very quickly kind of go into it and say, well, what if I make this change? Or what if I make that change? How does it affect the software stack? Oops. All right, so yeah, in summary, we found this super convenient, a very quick way to get so much infrastructure around an Ethernet driver, coded up, developed, and all these surrounding software going. And as long as you hide the hardware details behind a good HAL, the same driver works on both platforms. And it's just things like, it's wrapping things like the PCI, actual PCI calls, the DMA mapping calls, the fact that you need virtual addresses, so when you're doing any kind of submissions to hardware, make sure the testing model gets the virtual address, and then the hardware actually gets the physical address. And then we can get into things like the what-if scenarios. What if this happens? What if that happens? So, all right, that's all I had. Any questions?
I stole the microphone along the way. Anyway, hi, I'm Dave Todd. I had 3 quick questions, one for the audience. Is there anyone here working on wireless technologies? Does anyone here use wireless technologies?
That was a trick question.
It was not a trick question because it seems to be a global blind spot that we are very dependent on wireless technologies, and yet we have no one really investing in it except me and my Make Wi-Fi Fast project. So if someday somebody would like to work on those, please talk to me. Second question, in your wonderful draft there, I didn't hear about BQL.
About BQL?
Yes. In my opinion, BQL is absolutely required once you move to real hardware, but you won't see a need for it when you're running in a virtual environment. It's 6 lines of beautiful, lovely code by Tom Herbert there.
I guess I will put that under the hardware modeling. It does not have to be an exact hardware model. It just has to have the essential elements which let you progress with your software. So it really gets into what are you trying to tackle at that beginning, any given point in time. And from there, are you going to wait for the real hardware? Are you going to wait for, you want to just play around with your software model? The BQL thing has not come up yet.
All right, my third comment. iPerf by itself really is not enough. You really need to be testing a wide variety of traffic.
iPerf 3 in this case, it's a lot of packets, it's a lot of data, which lets you cycle through your queues and roll them over very fast. And so you're getting into that logic. Are you handling rollover correctly? Are you supplying buffers fast enough? It's that kind of thing. It's not meant to be your complete end-to-end, end-all testing.
So let me rephrase the problem a little bit. So when I started a while back working on network drivers, I had a 2,000 line budget for a driver. How many drivers today fit into 2,000 lines of code?
My testing model is 7,700 and something lines.
Okay.
Right, sure.
How many production drivers fit into less than 100,000 lines of code? So
Well, what do you include in that? Because if you're talking about the hardware-software interface, I would say
all of the junk we're putting into drivers today. Obviously, these things have so much features, so much functionality. So I think, on one hand, this is fantastic. It's a great tutorial introduction to drivers. So I learned a lot. Let's suppose I was writing a driver from scratch. Mm-hmm. One thing I would do, and I would probably do this with any code I ever wrote from scratch, I don't write code from scratch. I just find some other code that looks like what I want and cut and paste it and then I'd substitute ENF for the name of my company, right?
That
So-
is an advantage to open source, isn't it?
Is that part of this? Do you have a reference driver that does this that we could potentially download and here put in how you contact the driver? Here, this is where you contact the hardware queues. Do you have something like that?
No, that gets into an extension that Jesse brought up earlier this morning. How much of driver code is truly unique versus could be pushed up into more library kind of things? And, eTool operations, for example, it is going to be, if you're pulling hardware stats, if you're doing software stats out of page pool, for example, yeah, it's all common code. But if it's hardware-based stats you're pulling, that's going to be hardware unique. I think that's a hard one to really answer. Do we have code that we're going to open source around this? We have a driver that's going to come out at some point. The testing model that exists would not, and you just basically look at anything that has a hardware reference was wrappered out, and the rest of the code is what it is. It was needed for our driver. So no, in a generic sense, but you'll see what comes out is super easy to wrapper into this model.
So there is one nice subtlety here that goes back to Dave points. Also, I think what we're going to talk about with some of Willem's standardization of offload features. Having a reference model is an interesting opportunity to do a best common practice, best current practice. Mm-hmm. So some of these things, there's multiple ways of doing these. Mm-hmm. Some are less preferred than others in some circles. And it would be interesting not just to have the hooks, but also if we could influence doing it the right way, I guess is the best way to phrase it.
Well, what is the right way? Because I've gone through the OCP.
The right way might be subjective, but we could have that discussion.
Yeah. Right.
Different
we are
ways.
bleeding into
it goes
that.
back to standardization.
I've also seen your comments around checksum handling, for example, and your history with protocol ossification as well.
Hey, David, thank you for presenting today. I had a quick question about why you chose this model of basically reinventing the wheel for a lot of the lower level stuff versus like using something like just a QEMU environment that has everything sort of built in where you can really talk to end hosts and talk to a real network or talk amongst yourself.
At the beginning of time, you have nothing. Mm-hmm. So what wheel did I reinvent?
Well, I mean, I feel like you had to reinvent a whole bunch of stuff around like dealing with the PCI layer and making abstractions that fake it for you, right? So, I mean, that's one way of doing things is to do the QEMU model. And I'm not saying it's the best one. I was just curious if what you had considered and why you didn't choose it. It's okay. I'm not mad.
Like I said, at the beginning of time, there was no way to use QEMU. Right? Because there was, when you're building a driver, you're building it for a specific piece of hardware, but then you have to make your hardware visible to a software stack. In the case of Linux, it's PCI device operations and it's the Netdev operations. And then how you implement those are going to be specific to what you're doing with your hardware.
Right.
So maybe actually I'll jump in there and address a couple of different things that came up. This thing is really just the data path. I think, Jesse, the most important thing of the answer to your question is there was no PCI. I think that's the important part. There was no PCI definition even. This was really just to get the packet path going as quickly as we could so that we could come up with speed, measurement, what works, what doesn't work, and answer those questions very, very quickly. PCI, control, device creation, sub-function, all of that came later. And to the point of somebody asking, can we standardize this, right? So there are two parts to this. There's the actual device driver bit that will be open sourced, whatever. And then there's the testing backend. In the testing backend, there's infrastructure, and then there is how our hardware works. Clearly, that's not going to be something we want to go open source because that's our device model. But the interfaces, if somebody wants to come do an internship with us and try to build a package that somebody can go build a new testing backend against, we would be very happy. So come talk to Dave or me and we'll enable that. No, I'm serious.
Actually,
I mean,
no, definitely come talk to me.
it would be a good thing to go build. Yeah.
Here, one quick thing though.
this is Linux only. So if you're doing device drivers that you have to do anything other than just Linux, that's where the QEMU ends up becoming much more scalable, just from experience. So that, and I don't know, I think to some extent it's the learning curve on QEMU, I think is more the blocker for you guys than, or was the blocker for you guys than anything else. Because to some extent,
No, I knew QEMU. I've been playing with QEMU since like 2006. So I knew QEMU well.
because creating a new device takes about 5 minutes in the
Yeah,
QEMU
Saeed
code.
said that as well. You can fork the QEMU source code, you can copy
Right.
clone it, and you can put your build infrastructure in place, and you can set the ops around QEMU models. You have not implemented a QEMU model at that point. E1000 is a good start point if you have a pure CSR-based model. What if you have an image, a messaging-based model between your hardware, software?
Well, yeah, then you have to start, but that's the thing, is you had to go
That's-
implement
that's
that in
my
your,
point. So you can't use VirtIONet as a template, and you can't use E1000 as a template. You almost need.
well,
a
no, that's the
blending.
thing, is to some extent, you're going to end up with a PCI device at some point in your model anyway.
Sure.
So all I'm talking about is basically you lobotomize it to the point where it's a device ID and an MMIO region, and
That's
you can
not the
put whatever
point.
you
So-
want in the MMIO.
So we've done the transition, and so people get stuck on this idea that QEMU provides this lot. MSIX is not unique to your device.
Right.
The PCI operations are not unique to your device. The
Right.
DMA mapping is not unique to your
Right.
device. That's just pure overhead when you're trying to get started. And what you're worried about is, what are your descriptors? What do you want from hardware on an RX side? What do you want to tell hardware on a TX side?
Right. I'm
Right?
just,
That's the important things from day one.
right. But see, that's the thing, is that's
The
like,
actual location of a PIDX for a queue, that's detail. That
well, right.
comes later.
That's what I'm saying, is you can ignore most of that. It's just,
I
you
think you
create
guys are-
stuff just to have something to
You,
hook on
you
to.
guys are actually agreeing. So just what David said is, so we are switched to a QMU, or we have a full QMU model as well, and that's a
Yes.
much more. It's got more complexity also in the runtime, right? Running a multi QMU instance
Exactly.
requires. This is super lightweight. This is what everybody actually. The thing that David mentioned very quickly. All of us run this in a partition on our Chromebooks, and we can run tens of them without having any real issues. Run one of those with QMU, and we are looking for a big server right away.
Yeah.
Right, it's just different levels. Basically, this would be what I consider one level above QEMU. Then you have QEMU, then you have actual silicon simulation, which is even slower but more exact, and then you get to actual hardware in the end.
And so to get that full model, that's someone's job. That's someone's like full-time job, is to go create that full QEMU thing. I wrote the simple instance in like an hour. I'm off and running, worried about my side of it. And as long as I got the front end right, the interface correctly, the real model coming, or the better improved high fidelity model coming in, okay, there's more CPU cycles taken up, but I already had my stuff coded, and it just worked. And so I'm able to do my job at my pace, not relying on what is the schedule of this other team. When are they going to be ready? When is this team going to be ready? And how is this all integrating together? So now we're just focused on the integration of things, not the waterfall serialized development cycle.
First of all, thanks for all the talk. It's great information. I actually have grown QEMU models in the past, and I remember before doing QEMU, we tried something like this, but we didn't have the knowledge. So, having this information around is going to help a lot of teams. I definitely see the value because, as you say, multiple QEMU instantiation and the cycle to change QEMU model and do a new change and deploy and so forth is definitely more complicated. Got a question for you. How do you handle, how stable is your modeling? Your model is basically run the kernel, so you're risking that if you screw up, then you just basically nuke your own computer, right? So at some point, that happens at some point, right? So eventually you get stable enough that you can run fast and your models are not that dangerous to yourself.
Well, it is run inside of QEMU instance.
Okay. Oh, so you run a QEMU.
Yes.
Yeah. So.
But it's
okay.
not a QEMU device
Yes.
model.
Okay. Yeah. So
Just
you-
like any kind of development stuff, like I always do kernel-based development inside of a QEMU instance, because if I blow it up,
Yeah. Okay.
delete
So
the
you
image,
just unbox yourself. So.
own another one, do the
Yeah.
set up and go.
Right.
Yeah.
Appreciate it. Thanks.
Yeah, so even the demo that I showed, that's a Ryzen server with a QEMU instance on it, so that again, I don't destroy development servers while I'm making mistakes doing a driver, yeah.
Yeah. Okay.
Hi, David. I have a question.
Yep.
Hi. So yeah, I'm David. I know your original motivation for this is for companies that want to build new hardware, but do you also see this as a way to have self-contained Linux testing framework? Because, for example, I'm working on Zero Copy RX, and we are kind of looking for a way to test some of the things that we're doing, like because we're messing with the RX queue, and we're kind of hacking VF right now, but that stuff can never go upstream, right? Because VF is production. So we're kind of looking for a way to kind of test the work that we're doing, reconfiguring queues, controlling, testing for hardware failures. Like, what if header splitting fails?
Yeah.
What if flow steering fails? Right? We want to kind of write test cases that exercise our code, and I kind of see what you're doing as like exactly the sort of stuff that we're looking for.
Yeah, so you probably saw the ZCTAP reference earlier, right?
Yeah.
So when Jonathan was working on that, I was able to take his code and very quickly adapt my software testing model to his expectations, and then get it coded up and working within, I don't know, like a day and a half.
Yeah.
So that is a huge part of it, is speed, because if you were to wait for some QMU model to come around and some other team who's got this big fidelity model and they all the details of it, and you're just wanting to do something quick, but yet it's going to take you a month to wait for them to get it scheduled and whatever. So that is a huge motivation for this. And so when the IOU ring set comes out, yeah, I'll immediately port it to this and see how it's going to affect us. What does it mean? What happens when this, whatever bug happens? Yeah, that is the point of it.
Cool. What's the status of this? What's the status? Is it merged upstream? Does it come with like some sample software models that we could use
No,
for?
it's strictly our device model.
I see.
When I look at how much of the code is unique to our device versus the infrastructure, like I said, it's that file is like 7,800 lines of code. I would say probably 6,000 of it is related to how our hardware works.
I see.
And so the rest of that is going to be things like spawning the kernel thread, doing the fake initialization for a PCI device, the platform malloc, some of the cleanup code, the wrappers for the adder addresses and things, virtual addresses. What's that? Yeah, some of the infrastructure, but without that, I mean, it's, like I said, the overwhelming majority of it is a device model.
We could restructure.
Click on this.
What can we restructure to have
Yeah.
a callback base?
Yeah.
The idea is very good, right? If this was something that we are using it as a quick test today, right?
Yeah.
It would be a very interesting Linux kernel test framework.
Yeah.
So I think there's a remote question here, but maybe I miss. You can look up there.
Oh, yeah. I can have one over here.
I don't know. What's the question there?
Oh, so it says, how would you like to see your approach applied to TCP kernel bypass techniques? It'd simplify a lot of assumptions made with respect to Linux, network stack, snappy, et cetera. As a Linux kernel developer, I don't have much interest in kernel bypass. So, but to be fair, yeah, it really is. You could easily take the same approach. Like, I haven't taken the time to do XDP and AFXDP kind of hooks. That would be an example of a kernel bypass. I haven't done the DPDK style driver, whatever it needs to interface with it. But yeah, I guess again, if you've got your hardware model and these are the things you're looking to do, you just have to write that software that exposes it. So, yes, I guess I don't consider that kernel bypass since we go through the networking stack. Sure, semantics. No, I do think the intent is there, and that's why I brought it up in NetConf when Sabrina was asking about testing hardware offloads. It's like however much you want to test is how, what kind of fidelity you put into your device model, right? And so it does allow a lot of the testing of the software infrastructure to me, and it's a very simplified environment.
Yeah, I think we need to wrap it up.
Yep.
It's break time.
All right.